Okay, so the talk is about how do exponential size solutions come up in semi-definite programming. This is joint work with Alex Tuzov, who is my PhD student, and we're excited about this work. So I hope you are going to like it. So let's start with linear programming feasibility as a warm-up. So the question I'm asking is, given this linear system of inequalities, is there an X which is a feasible solution? And here the A is a matrix, B is a vector, and they are given by integer entries. And I only want to know whether there exists a solution to this linear system of inequalities. And we know that if there is a solution, then there is one which has polynomial size. So if this problem has a feasible solution, then there is a feasible rational X bar in which the entries have numerator and denominator that are not too large. In particular, the size is at most n times log L, where n is the number of variables and L is the largest entry in A and B. And how do I get to this result? I'm going to use Kramer's rule at an extreme point of this linear program or linear inequality system. So the corollary of this, suppose I just want to know whether there exists a feasible solution, then a way to do that is I'm going to compute one, and that's reasonable because I can describe that solution in polynomial space. Now let's go to SDP, semi-definite programming feasibility. In that case, I'm going to be curious whether there exists an X solution to this linear matrix inequality. Here, the AI and the B are symmetric matrices, and the S greater or equal than 0 for any S matrix means that this S is symmetric and positive semi-definite. This is a far-reaching generalization of linear programming. There are many, many papers. And the point that I would like to address is that it may have solutions which have to be of exponential size. This is shown by this classic example of Khachiyan. So we have m variables, and we start out with saying that xm has to be greater or equal than 2. And after that, I keep squaring the variables. So I say that x1 is greater or equal than x2 squared, x2 greater or equal than x3 squared, and so on and so on. And if I do a little algebra, then by induction, I can see that the x1 has to be greater or equal than 2 to the 2 to the m minus 1, where m is the number of variables. What does it say about the size of x? I take the log, and I see that the log of 2 to the 2 to the m minus 1 is 2 to the m minus 1. So the size of x has to be at least 2 to the m minus 1. In other words, even the size is exponentially large. And this is a quadratic system of inequalities. But at the same time, I can write it as an SDP. I can write these quadratic inequalities by 2 by 2 linear matrix inequalities by putting the xi on the diagonal and the xi plus 1 on the off-diagonal element. Okay, so I should stop here and see if there's a question.
So the question, so the form of the SDP on the previous slide, and this is different in terms of like structure, right?
Yes, so this is a block structured SDP, right? Because I have to put together a bunch of small SDPs, a bunch of 2 by 2 SDPs. But at the same time, I can make this bunch of small SDPs into a large SDP because I can take these 2 by 2 blocks and I can put them onto to be the diagonal block of a large matrix. Mm-hmm. So I can rewrite this in a standard form.
Okay.
So just like linear programs have a standard form, SDPs can be put into a standard form.
Right.
So if I want to see what goes on in this problem, I can picture it. So instead of saying that the x3 is greater or equal than 2, I'm going to say that the x3 is between this upper and lower bound. And after that, the x1 greater or equal than x2 squared, x2 greater or equal than x3 squared. So we can see that the x1 grows quite drastically when the x3 grows. Now we come to this major open problem, which is SDP feasibility in P? And this is a major open problem. It's open even for quadratic constraints. And what is the main dilemma there? In SDPs, if I have a solution which has to be of exponential size, then how do I prove in polynomial time that exponential size solution exists? I mean, I cannot do it by simply writing it down, because even that would take exponential time just to write it down, let alone computing it. So that's the major dilemma. And this is an open problem that has been open for 30, 40 years, depending how we count. And I should emphasize that this is even open for quadratic constraints. So to some extent, we can view this as a very fundamental problem as to what is the difference between linear and nonlinear, because quadratic is just a little bit more difficult than linear. So we can see that this problem already shows up in quadratic problems, which are only a little bit more difficult than linear ones. Now, from this major open problem, we can derive two open questions. The first question is it possible to represent these large solutions in polynomial space? So can I somehow convince myself that a solution is really a solution, even though actually writing it down would take exponential space? And the Khachiyan example, it gives us some hope, because in order to convince myself that the 2 to the 2 to the m minus 1 is indeed a solution, I don't have to write down the 2 to the 2 to the m minus 1. I can just do some kind of symbolic manipulation. I can see that 2 to the 2 to the m minus 1 with some suitable x2 and with some suitable x3 and so on is a feasible solution to that linear matrix inequality or to that quadratic system of inequalities, without having to write then the 2 to the 2 to the m minus 1, which would take a lot of space. So in other words, the system provides a certificate by doing some symbolic computation. The second question is, are large solutions common in semi-definite programs? Now to that, the answer seems to be a no. There are several reasons for that. The first is that they don't come up in linear programs. Linear programs are, of course, SDPs. And they also do not come up in typical SDPs in the literature. So for example, in the max cut SDP, which is our typical favorite SDP, they don't show up. On the other hand, we can also eliminate them even in the Khachiyan problem by a very slight change. So for example, what I can do is I can replace the inequality xm greater or equal than 2 by this new inequality when the 2 is replaced by 2 plus xm plus 1, where xm plus 1 is a new variable. Now I can make the xm plus 1 to be something negative. Let's say I can take it negative 3, then the xm doesn't have to be larger than negative 1. And then if I continue this chain of reasoning, then I can see that the x1 doesn't have to be large anymore. Now, the other way of getting rid of the large solutions is I can do some kind of random linear transformation. I can replace the x by gx, where g is some random dense matrix. So I can do this linear change of variables, and then the Khachiyan problem becomes a complete mess. So if I do a linear change of variables in an SDP, it is still going to be an SDP, but it becomes a very messy one, and I just won't be able to see any kind of structure anymore. So I should stop here and see if there is a question. So, but I can kind of guess or state that apparently it seems like the common consent is that large variables in SDPs are rare, so they don't really happen a lot. So I would like to see, is there any question?
If you do a chain of variables, then for the Khachiyan's example, you can still solve it to get the solution which is not exponential large, or?
That's a good question. It's one would have to try it.
Mm-hmm.
One would have to try it. It's a good question whether if you have that nicely structured. I mean, if you put that into MOSEC, I think it's going to just say that there's an overflow because you cannot store that large numbers. But it's a good question whether if you do this random change of variables, is it going to be something better?
Mm-hmm. Okay.
That would be interesting to try, actually.
Right, right.
So the main result is, which is informal, that actually every strictly feasible SDP can be made into a Khachiyan type SDP as follows. We need a little bit of background. It's not going to be too much. I'm going to look at this dual system, which is y positive semidefinite, ai dot y is equal to 0 for every I. So this is kind of like a dual SDP. And I'm going to look at the singularity degree of this dual SDP. What is singularity degree? It's the minimum number of so-called phase reduction steps to certify what is the maximum rank positive semidefinite matrix in this dual system. Now, if you know what is phase reduction, that's great. Now, if you don't, then that's not a problem either. The only thing we have to know is that k is a non-negative integer parameter, and it's less or equal than 1 when the SDP is a linear program. Of course, I can make that SDP into a linear program, for example, by making the matrices diagonal. So this is all the background that we need. And we are also going to assume one more thing, that the SDP is strictly feasible. So there exists an X so that this linear matrix inequality holds strictly, so that this affine combination of matrices is positive definite. So I'm going to assume that, and it turns out that these assumptions are going to be minimal. And here's our informal theorem 1. So after a linear change of variables, X is replaced by mx, where m is a suitable invertible matrix. If X is strictly feasible and xk is large, then this following chain of inequalities holds, where the alpha exponents are bounded between two extremes. So the upper bound is at most 2, which is to be expected because that's what happens in Khachiyan's example. And the lower bound is larger than 1 on every one of the alphas. It's k divided by k minus 1, k minus 1 divided by k minus 2, and so on. It goes all the way up to 2. So the dj and the alpha j are constants that depend on the ai and on b, and on the large m minus k variables that we consider to be fixed. So in other words, after a linear change of variables, I can create a Khachiyan type SDP from any strictly feasible SDP. That's the gist of the main result. And the assumptions that we make are minimal. I'm not going to go into every detail, but that's in the paper. So I should stop here and see if there is a question.
One question is the matrix M is like you just show that it exists a matrix M, right?
Right. So this is a constructive proof. So we can show how to construct the M, but to do it computationally, we would have to solve SDPs in exact arithmetic, which in general we don't know how to do. So it's a constructive proof. On the other hand, there is going to be some concrete examples in which the M is just an identity matrix. So we don't have to do anything at all, and the SDP is going to be automatically in this Khachiyan type shape.
Mm-hmm. But those examples, it's rare, or they are...
So there is only 2 of them, and one of them is something that we created. So it comes from something that's concrete. Comes from polynomial optimization, which people have studied. And we show that even in that example, this hierarchy shows up without a change of variables. The other one is due to a computer scientist, Ryan O'Donnell, and he also came up with an SDP that has large solutions, and we can show that his SDP fits into our framework.
Okay, and alpha j here need to be alpha k. It need to be a rational number, or it can be a real numbers.
That's a good question. You see, I think they have to be rational.
Okay.
I think yes. They are going to be rational. I haven't even thought about that, but if I think about it a little bit, they have to be rational. Yes.
And D can be just positive real numbers.
Yes.
Or,
They have to be positive, otherwise this sorting doesn't
mm.
make too much sense.
But
Yeah,
they are rational as well, or is this can be
you can choose them to be rational.
okay.
You can choose them to be rational, and that's just because the rationals are dense, in the set of real numbers.
Right.
But the alphas can be or rational, can be chosen to be rational. Yeah. So the corollary, if we start playing with those inequalities, we start to see what happens if the alpha j's are at the upper bound. So the all alpha j are equal to 2. Then I can derive that the x1 is greater or equal than constant times xk to the power of 2 to the k minus 1, which is exactly what happens in Khachiyan's example. Now, if the alpha j's are at the lower bound are strictly bigger than 1, remember that? Then I can derive that the x1 is greater or equal than constant times xk to the power of k. So let's see what happens.
One more questions.
Yep.
So in order to get exponential large variables, and you need xk to be greater than 1, right?
Yes.
You need to put that constraints, right?
Yes.
Otherwise, not okay.
So the theorem says that this is true if the xk is large enough.
Right. Okay.
Which kind of makes sense, because even in remember that even in the Khachiyan example, if I replace the xm greater or equal than 2 by just saying that the xm is greater or equal than 1/2, then the whole logic collapses and the x1 doesn't have to be large anymore.
Yeah.
So let's look at whether these extreme possibilities can really occur. So the worst case example is the Khachiyan SDP. I'm going to look at this, I'm going to demonstrate this for 4 variables. So there is this 5 by 5 linear matrix inequality. So this matrix has to be positive semidefinite. And I can look at the red subdeterminants, the blue subdeterminants, and the green subdeterminants. Meaning red subdeterminant is the subdeterminant which has 3 red corners, the blue is which has 3 blue corners, and so on. And the red corners imply that x1 is greater or equal than x2 squared, then x2 greater or equal than x3 squared, and x3 greater or equal than x4 squared. So the exponents are the largest possible that can come out of the theorem. Now let's see whether we can get the exponents to be minimal. And let's look at this mild SDP. Here, again, I look at the red subdeterminants, blue subdeterminants, and green subdeterminants. And I get the inequalities x1 times x3 greater or equal than x2 squared, x2, x4 greater or equal than x3 squared, and x3 greater or equal than x4 squared. Now, these are not so nice as in the Khachiyan example, because I have xi, xj on the left-hand side. However, I can do a little algebra, and I can derive inequalities in which the left-hand side only has an xj in it, and the right-hand side has xj plus 1. So specifically, I can derive x1 greater or equal than x2 to the power of 4/3, x2 greater or equal than x3 to the power of 3/2, and x3 greater or equal than x4 squared. So in this, the exponents are the minimal that can happen in my theorem. So both extremes can be achieved, both the upper bound and the lower bound can be achieved. And if I want to picture this just with 3 variables, and I added the normalization x3 between 2 and 0 just for normalization to make things better visible, then I see that in the Khachiyan example, the x1 grows much faster when the x3 grows as opposed to the mild SDP. So I should stop here and see if there's any question.
There is one question. So if you go from the worst case to the my case, and how many combinations that you get?
Yeah, that's a good question. You can count it. I mean, there is going to be the result stated, there's going to be a recursion later on in which we are going to find out how to compute the alpha j's. So I think one can count it. I think one can count it.
Okay, so the numbers would be finite, but could be exponential large, right?
I think they could be exponentially large, exponentially many possibilities for the exponents.
Right.
But there is going to be definitely finitely many possibilities.
All right.
So the proof idea. So first there is this issue of reformulating, in other words, changing variables. So there is this crucial part of the result that we have to change the variables in order to get to an SDP in which I can find this Khachiyan type hierarchy. So I'm going to change variables to get an SDP, which I'm going to call SDP prime. Second, from this SDP prime, I'm going to derive messy quadratic inequalities such as these. So here we have, this is quadratic, but instead of just having x1, I have x1 plus a linear combination of things which are larger numbered, larger indexed than x1, so x2, x3, and so on. So we can derive such messy quadratic inequalities. And in the messy quadratic inequalities, I can clean them up. In other words, I can suppress the larger numbered variables. I can suppress the x2 and the x3, and I can suppress the x5. So I'm going to get something like x1, x4 bigger than constant times x2 squared when xk is large. So the point is to suppress the larger indexed variables. And then finally, I can do some elimination procedure to make sure that the inequalities look like xj greater or equal than constant times xj plus 1 to the power of alpha j plus 1 for every j. And after that, we can find a recursion to compute the exponents. So these are the main steps. And the first step, which is probably the most important one, that I can reformulate my SDP into this SDP prime, which has this special format. So the first constraint matrix has this small identity matrix in the upper left corner and lots of zeros elsewhere. And the second constraint matrix has arbitrary stuff in the first R1 rows and columns, and then a small identity matrix. And then it keeps going like that. So in general, in the ith constraint matrix, the first R1 plus 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 Ri minus 1 rows and columns are arbitrary. And then there's a small identity matrix. And the sizes of these identity matrices are positive. Those are the Ris, R1 through Rk. And then there is some other matrices here, xi times ai prime plus b prime, and those don't really matter what they look like. Now, to be 100% precise, to get to this normal form, the only thing that I did is not just a linear change of variables, but I also used similarity transformations. So I was permitted to replace the matrices AI by T transpose AIT, where T is some invertible matrix. So to show the main idea here, I'm going to show how from this SDP prime, I can derive messy quadratic inequalities. So I'm going to show this by an example. So I'm going to focus on the x2, x3, and x4. And then there is this dot, dot, dot. The dot, dot, dot means that there is some combination of the x5 times a5 prime, and so on and so on. And I'm going to look at these circled entries, which are going to give me a 2x2 subdeterminant. And I know that since this matrix is positive definite, the 2x2 subdeterminant has to be positive. So I'm going to look at this 2x2 subdeterminant, which is x2 plus 2x3 plus 5x4 plus dot, dot, dot. Dot, dot, dot means a combination of x5 and so on and so on. And then it's multiplied by x4 plus dot, dot, dot. That comes from this lower right entry. And then the off-diagonal entry gives me 4x3 plus 7x4 plus ... squared. So from a positive definite matrix, I can very naturally derive quadratic inequalities just by looking at 2 by 2 subdeterminants. I don't even have to look ever at 3 by 3 subdeterminants. It's not even necessary. And the ... as I said before, means a combination of higher numbered variables. And the cleaned up version of this, I can suppress the higher number terms. So I'm going to get from the x2 plus 2x3 plus 5x4 plus ... I'm going to get x2. And then from the x4 plus ... I'm going to get x4. And then from the right-hand side, I'm going to get constant times x3 squared. And this whole thing is going to be true only if xk is large enough. So that's the basic idea. So I should stop here and see if there's a question.
So in order to get the form SDP framed, you need to assume the problem to be strictly feasible.
Yes.
Right?
Yes. Well, no, I mean, just to reformulate the problem, you don't have to assume that the problem is strictly feasible. But to derive the inequalities, for that you do have to assume that the problem is strictly feasible. So that reformulation into the SDP prime format, that works for any SDP.
Right. So here is the coefficient alpha k it's computed. Can you go to the next page?
Next page. This one?
No, previous.
Yeah.
So the matrix T here is again is not like is contracted or just show it exists a matrix transformation.
Again, it's the same story. So in order to compute the T is the same story as to compute the M. So I know that it exists. I can give a constructive proof. And I also need to actually compute it. We have to solve SDPs in exact arithmetic. But again, there is going to be some concrete examples in which you don't need a T and you don't need the M.
Okay.
So in other words, from a strict SDP, one can derive quadratic inequalities just by looking at 2 by 2 subdeterminants. Now, okay, does this make sense? Are there any more questions?
No, it's clear.
Clear. Okay, so then how do I compute the alpha j plus 1 exponents? There's a nice recursion for that. In particular, I can compute these by this recursion going backwards. So first I compute the alpha k, and then the alpha k minus 1, and so on. So in general, the alpha j plus 1 is computed as 2 minus 1 over a product of the alpha j plus 2, alpha j plus 3, and so on, alpha tj plus 1, where tj plus 1 is a number that I'm going to define a little bit in a hand-waving manner. But let's notice that firstly, this is something like continued fractions. So this is continued fractions are something that we know from number theory, and it's kind of interesting that they show up in SDP. And tj plus 1 is the index of a rightmost block in the linear matrix inequality where the xj plus 1 shows up. Again, this is still a bit of a hand waving, but I'm going to give some very concrete examples. So what I can see from this definition is that suppose I shift the xj plus 1 to the right, then the tj plus 1 is going to increase. And if I do that, then I'm going to multiply more terms in this denominator, and then the alpha j plus 1 is also going to increase. Right? So that's the general idea, and I'm going to show this specifically through an example. So we start with this mild example, with this mild SDP. So this matrix has to be positive semidefinite. I left out the curly inequality just to save some space. And from this linear matrix inequality, I managed to derive the exponents 4/3, 3/2, 2, In other words, the x1 is greater or equal than x2 to the power of 4/3, x2 greater or equal than x3 to the 3/2, and then x3 greater or equal than x4 squared. Now let's shift the x2 a little bit to the right. Okay, then see what happens. Then the 4/3 became 5/3. So as soon as I shifted the x2 to the right, its exponent went up. And then I'm going to again shift the x2 to the right, and its exponent again went up. So the alpha 2 became 2. So if I go from the left towards the right, the inequality x1 greater or equal than x2 to the power of 4/3 became x1 greater or equal to the power of x2 to the power of 5/3, and then that became x1 greater or equal than x2 squared. So shifting the x2 to the right made the exponent larger. It was actually monotonically increasing. So again, I should stop here and see if there is a question.
So from the contraction of alpha k, alpha z, we can see it gives us rational numbers, but it's also related to the location of x, right?
Yes.
It's so how is it related to that one?
Well, that was in the previous one, you see, here. So the tj plus 1 is the position of the xj plus 1, is the rightmost position of the xj plus 1.
Oh.
So when the tj plus 1 gets larger, then that means that I'm going to multiply more alpha j's in this denominator, and that means that the alpha j plus 1 is going to get larger.
But you don't have the formula for a constant behind in front of xj plus 1.
No, that we haven't computed. I think that would be probably messier, or it's probably not that. I mean, maybe one can do that too. That's such a good question. Maybe one can compute exponent the formulas for the DJs as well. Okay, so now I'm going to look at a connection to Fourier-Motzkin elimination, which is something that we know from linear programming. And this connection is interesting because SDPs are, of course, very nonlinear. So we can view this whole process of deriving these inequalities as a variant of Fourier-Motzkin elimination, or as an application of Fourier-Motzkin elimination. So let's start. I'm going to show this through an example. So suppose I start with these quadratic inequalities. Now these quadratic inequalities can be made into linear inequalities because I can take the logarithm on both sides, and I can call the log of xi to be yi. So the x1, x3 becomes y1 plus y3. The x2 squared becomes 2y2, and so on. So I took the log, and from the quadratic inequalities, I obtained linear inequalities. And then on this, I can do some elimination. I can add positive multiples of an inequality to another inequality. So for example, if I add 1/2 times the last inequality to the middle inequality, I get y2 greater or equal than 3/2 times y3. And then this linear inequality can be translated back to the quadratic space, and I get x2 greater or equal than x3 to the power of 3/2. So this is not necessarily extremely important because I already know how to compute the exponents, but it's an interesting connection that computing these exponents is a little bit the same thing as Fourier-Motzkin elimination.
It's question before you move on.
Yep.
So here you have a constant in front of x, the right hand side, the inequalities here. then you take logs. Is it the inequality is going to have a constant,
Then it's
right?
going to be a constant, yes. But you can still do the same thing.
But then the constant is going to be a log, right? Terms.
That's right.
Meaning, yeah, so it's log smaller than,
Yeah,
meaning that
yeah.
it's a constant, it 8 and it's going to be like 3, right? Instead of,
That's correct. Yeah, 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 yeah.
so that's makes the numbers getting smaller.
Yes.
So in that case, it's also affects the solutions in terms of like the size of the solution, because because when you make the numbers getting smaller, it also like the solution also getting smaller, right? So
Yeah, but what's wrong with that?
so what I'm saying here is because we are looking at some solution which might be exponentially large, but if you it probably depend on the coefficient of the problems. But
Yeah.
here we take the log, do the change of variable for the log, then the coefficient also like also need to be changed from, let's say, a to log a, right?
Yes, that's true. That's true. That's absolutely true. Yeah.
And so
But that's okay. I mean, then after, at the end, when I translate everything back to the X space, I'm going to get the same results.
okay, yeah.
So there's like a one-to-one correspondence. It's just kind of interesting to see that we can do this by Fourier-Motzkin elimination.
Okay, that's right.
Right? So now we come to this question: do we need this change of variables? Which is kind of like a question that comes up a lot. Okay, so why do you need this change of variables? This looks so unnatural. So first I want to argue that this is natural, because if I do a change of variables, a linear change of variables, that makes a complete mess even out of the Khachiyan example. And after that, I will not be able to prove any kind of hierarchy or large variables, even in the Khachiyan example. So if I'm permitted to do this change of variables, then, so if I do that in the Khachiyan example, then I might have to do the inverse operation to undo this mess that I created. But sometimes it turns out that actually I don't have to do any kind of change of variables. And I'm going to show two concrete examples for that. So first, it's a kind of a classic example. Suppose I want to minimize an even degree polynomial. It's a univariate polynomial. And what I can do is I can rewrite this as SDP using the sum of squares technique. And I'm going to look at the dual problem. And I'm only going to show the case when n is equal to 3. So the univariate polynomial is degree 6. So then I get an SDP, a dual SDP, which looks something like this. And I can see that this problem is automatically in our SDP prime format. So in other words, the Y6 has a coefficient matrix so that the 1 is in the upper left corner, and then Y4 has some arbitrary stuff in the first one row and column, and there is a small identity matrix here. And the Y2 continues like that. It has some arbitrary stuff in the first 2 rows and columns, and there's a small identity matrix there. So in other words, this problem is exactly in the form of SDP prime without having to do any kind of change of variables. And the corollary is that the Y, which has 2n components, is feasible in that dual SDP. Then there is this nice hierarchy among the Yi's. So the Y2n is upper bounded, is lower bounded by a power of Y2n minus 2, and so on and so on. And if I combine those inequalities, then I get that the Y2n is greater or equal than the Y2 to the power of n. And it's interesting that this problem has been looked at for quite some time, but somehow this doesn't seem to be known. Okay, are there questions?
Do you require Y2 to be greater than 1, or how Y2 constraint on y2?
No, you don't. You don't. So in this case, you don't need this whole story of xk has to be large enough, because this is so clean that we don't need any of that, any of those complications.
Then is it not clear if the y2n is exponential large, right? It depends on y2.
Right. So it's lower bounded by the nth power of y2. And of course, if the y2 is large, then the y2n is also going to be much larger. So the other example comes from computer science. Suppose that I want to certify that this polynomial, which is a linear polynomial, is non-negative for all xy that lives in K, where K is some very simple set. So I'm not going to go into every detail, but K is a simple enough set so that one can convince himself or herself that this linear polynomial is indeed non-negative for all the xy which are in that K set. And the resulting SDP is going to look like this. Without going into too many details, I'm going to define the EIJ to be the IJ unit matrix. And then I will see that it's exactly in the form of SDP prime. So SDP prime is that normalized SDP. And so this SDP is in that form without having to do any change of variables, any similarity transformations, and anything like that. So it essentially yields Khachiyan's example. So this is a second problem from the literature in which we can show that it's already in that SDP prime format without having to do any kind of change of variables.
So this example is look like separation theorem or?
Separation theorem, sorry, what do you mean?
So it means that we need to separate the set K from, the origin or whatever.
No. It's simpler than that. It's just basically you want to prove that a polynomial is non-negative for all xy which lives in a certain set, right? So the sum of squares technique, if you don't have constraints, it just wants to certify that a polynomial is non-negative, and the way it does it is that you write that polynomial as a sum of squares. You write it as sum of I fi x squared. If you can do that, then you can be sure that that polynomial is indeed non-negative. And if you have a constraint, then you have to somewhat take that constraint into account.
Yeah. So, okay. I have not thought about this, but we'll see.
Okay, so then now we come to a point which we are quite curious about. The question is, how do we certify exponential size solutions in polynomial space without computing them? So here's the idea. So look at this reformulated problem again, right? So this is SDP prime. Now suppose that I'm given xk plus 1 and so on xm. So we are given these m minus k lost variables, so that I know that there exists x1 through xk, so this problem is strictly feasible. Now, how can I convince myself that this problem is strictly feasible? In other words, how do I convince myself that the x1 through xk actually exist? So what I can do is I can prove that the x1 through xk exist without having to compute them. So how do I do that? Well, I could compute them in reverse order, starting with xk and then xk minus 1, xk minus 2, and so on. And the way I do it, I'm going to make larger and larger lower right corners of this matrix to be positive definite. So we start with this matrix, the sum of xi ai prime plus b prime. So we start with this Z matrix, and I know that this corner is positive definite, right? Now after that, I'm going to add the multiple of the AK prime. So I'm going to add xk times AK prime, and xk is sufficiently large. And the result is going to be a matrix so that this lower right corner is positive definite. So I made this lower right corner, which is positive definite in the Z, to be a little bit larger, and it is still positive definite. And then I'm going to add the multiple of the AK minus 1 prime to make an even larger corner to be positive definite. So I'm going to make this corner to be positive definite, and so on and so on. And I know that I can do that because the AK prime is an identity matrix, which is here. So if I add a sufficiently large multiple of the AK prime to this matrix, then this lower right corner is going to be positive definite. So the structure of the AI primes makes it clear that I can carry out this computation, but I don't actually have to numerically carry out the computation because I know just from the shape of the AI prime that this computation can be carried out. So I don't know whether this makes sense.
So this actually comes from the Schur complement, right?
Exactly. You can view the Schur complement, but actually one doesn't even have to go to Schur complement. One can just go to the definition of positive definiteness that for every U, the U transpose AU is positive as long as the U is non-zero.
Right. You don't need to compute it by Schur complement, but it's just by contraction you can do that. Right?
Yeah. So the shape of the matrices makes it clear that these x1 through xk exist, right? And I don't have to carry out the numerical computation. I can just prove with pencil and paper, and I can see that these x1 through xk, they actually exist.
Yeah.
And then the question that comes up is it true that every SDP which has large solutions is in this regularized form? And perhaps I have to permit a simulated transformation, but that doesn't affect the size of the variable. So this is a big question, and this is what we think could be really interesting to help to solve that problem. I mean, can we certify every time that we have a large solution, can we certify that large solution in polynomial space? In this particular special case, we can do it. Can we do it every time? That's the question. Okay, are there questions?
So the large solution because adding a large number every time you compute it, or?
Well, the large solutions are because of this whole machinery that we developed in the paper. So that you have those 2x2 subdeterminants. So anytime there is a strictly feasible solution and the xk is large, that 2x2 subdeterminant has to be positive, and then we can push through that whole argument, right? So the large solutions happen because of that theorem.
Yeah.
But the point is that the x1 through xk are the variables which are large, and the point is that to convince myself that they exist, I don't have to compute them.
Yeah.
Okay, so the conclusion is that we have this issue that in SDPs we have exponentially large solutions, and this goes back to the famous Khachiyan example. And our main result is that we can derive a Khachiyan type hierarchy among the leading variables in every strictly feasible SDP after we do this linear change of variables. And we can compute the exponents using this neat formula, which is just like continued fractions. And we give a partial answer to this question: how do we represent exponential size solutions in polynomial space? And the point is that every known SDP which has large solutions is in our normal form, which is SDP prime. And we have a paper which is posted on archive. Comments and suggestions are definitely very welcome. So Thank you for your attention. And I'm happy to answer more questions.
I think I asked enough questions.
Okay. Well, so thank you so much.